So we have a ball here that is, the mass is 35 grams, and charge is 25 microcoulombs, and it's thrown upward with an initial velocity v naught of 22 meters per second, and it reaches some maximum height, right? So v naught is 22, reaches some maximum height with a final velocity of 0, and it covers a total vertical distance of 16 meters. And so we need to find what is the potential difference here, delta V. Alright, and we're assuming that, well, I think we're going to have to assume, for simplicity, that we're in a uniform field. So we need to find out first the direction of the electric force, right? So let's see, I'll tell you what, let's analyze this in terms of forces, right? So if I sum all the y forces, and let's see, we'll make up the positive direction, okay, for our sign convention, and down is going to be negative. Then I've got well, I got the gravitational force and the electric force, but I don't know what sign to assign them to. I don't know whether the electric force points up or down. So let's think about this for a second. I know delta S is 16 meters, and I know V naught is 22 meters per second, and V is 0. So let me find the acceleration real quick. Okay, that'll help. So what I get, v squared is equal to v naught squared plus 2a delta s. So 0 is equal to 22 squared plus 32a. Okay, so when I solve for a, I get that the acceleration is minus 15.125. Okay, that helps. So what that tells me is that the gravitational force points down, and the electric force also points down. Okay? Now how do I know that? Because if it were in free fall, the acceleration would be minus 9.8. And I put the minus sign there because we've decided that down is negative. Since the acceleration is greater than free fall, that means there must be an additional force pushing this thing down, and that's our QE. Okay, now, since the electric force points down, that means the electric field points down. Okay, and that's going to be useful when we're trying to find the change in potential in part B. Okay, so let's see. So now I can sum all my forces in the y direction and say that's equal to minus mg minus qe, and that's equal to ma. Okay, again, we're doing magnitude, direction, magnitude, direction. So let's see. That's what do we got here? That's minus 0.035 times 9.8 minus 25 times 10 to the minus 6 times E is equal to 0.035 times minus 15.125. Right? So if I solve for E in this mess, I get E is equal to 7,440 volts per meter. Okay? And we know from our analysis up here that it points down. Now the magnitude of the potential difference, delta V, the magnitude of the potential difference is just ED because it's a uniform field. So that's 7440 times the distance, which is, what, 16 meters? So that's 120,000 volts. Okay, now let me consider another way to do this problem. We could use work energy. Right? We could say that it's the sum of the works done by all the forces. So this is an alternative method. You don't have to do this. I've already done part A, but this is in case you did it with work energy. And if you did, then I'm a fan. So the only two forces that work here are the work done by gravity and the work done by the electric force. That's equal to the change in kinetic energy. Now, the work done by gravity, we can use minus mgh. Right? It's negative because it goes up and gravity points down. And let's see, for the work done by the electric force, we have to use minus q delta v, right? And that's equal to 1/2 mv squared minus 1/2 mv naught squared. And the final velocity at max height is equal to 0, so 1/2 mv squared is equal to 0. Alright, so minus mgh, so this is minus 0.035 times 9.8 times 16 minus 25 microcoulombs times delta V is equal to 1/2 times 0.035 times the initial velocity, 22 squared. Well, if I calculate delta V from this mess, I get 120,000 volts. Okay. And now here's the thing. So 120,000 volts. That means that VF is greater than VI, right? In other words, the final potential up here, we got a higher potential, and down here we have a lower potential. Okay. So the electric field points down, because electric fields point from higher to lower potential. And so in part B, that tells us that where is the voltage higher? Is it higher on the ground, or is it higher at y equals 16? The voltage is higher at y equals 16 meters. Now, we also could have deduced that it's higher back here in part 1, because when we first deduced that the electric field points down from our analysis over here, we could have deduced that the voltage was higher at y equals 16 meters as well. Okay, so either way you do it. You can either do it with forces, or you can do it with work energy, and the logic works out, thanks to being a uniform field.